Now let's go back to the prime number theorem. Recall that pi n is the number of prime numbers less than or equal to n. Then the prime number theorem says, roughly speaking, the counting function pi n increases like the analytic function n divided by log n. But the numerical experiments show pi n is not very close to n divided by log n. So we may ask the following questions. Can we calculate pi n accurately? Which function shall we use instead of n divided by log n? We want to have a better approximation to the prime number counting function pi n. Here is a table of the values of pi n and n divided by log n. For example, if n is 10 to the 10, the value of pi n is approximately 455 million. Whereas the value of n divided by log n is approximately 434 million. The ratio of these two values goes to 1 when n goes to infinity. But the approximation does not seem very precise. Here is an unsolved conjecture on the refinements of the prime number theorem. It is conjectured that the half the digits of pi n and LIN are equal. Here, Li is the logarithmic integral function defined by the integral from 0 to x of the inverse of logarithm. Perhaps you are not familiar with this function. The point is that the logarithmic integral function Li is a very nice analytic function whose definition does not involve prime numbers at all. It is an amazing conjecture that this analytic function Li counts prime number in a very precise way. It is a far-reaching generalization of the prime number theorem. Numerical experiments support the conjecture. Here is a table. If n is 10 to the 10, the value of pi of n is approximately 455,052,000. On the other hand, the value of LIN is approximately 455,055,000. It is a miraculous coincidence. The numerical experiments suggest the conjecture might be true. The theoretical background of the conjecture is already known. It follows from much deeper analytic properties of the Riemann zeta function. A complex number S which satisfies zeta of S is equal to 0 and whose real part is between 0 and 1 is called a non-trivial zero. The Riemann hypothesis is an unsolved problem concerning the non-trivial zeros of the Riemann zeta function. The Riemann hypothesis says every non-trivial zero of the Riemann zeta function has a real part 1/2. This is an extremely deep conjecture. If the Riemann hypothesis is true, then we can prove that half the digits of pi n and Li(n) are the same. Hence, we have an amazing generalization of the prime number theorem. So far, nobody knows how to prove the Riemann hypothesis. Today, the Riemann hypothesis is considered as one of the most important open problems in mathematics. It is one of the 7 Millennium Prize problems of the Clay Math Institute. It awards $1 million. I hope some of you will solve the Riemann hypothesis in the future. Let's summarize the topics we learned this week. First, we learned the basics on prime numbers. Every positive integer has a unique factorization into the product of prime numbers. There are infinitely many prime numbers. Both are fundamental results in number theory. Then we learned the prime number theorem. The number of prime numbers up to n is approximately equal to the function n divided by log n. But the approximation is not very precise. We learned the Riemann zeta function and the Basel problem solved by Euler. The equality between zeta of 2 and the square of pi divided by 6 was just the beginning of the mystery between prime numbers and zeta functions. Finally, we learned the Riemann hypothesis. Although its statement is analytic, it has striking applications to prime numbers. The Riemann hypothesis is one of the most important unsolved problems in mathematics. Next week, we will learn laws of prime numbers. It is known that prime numbers obey many interesting laws. We will learn basics on modular arithmetic, including Fermat's lattice theorem and Wilson's theorem. Then we will learn Fermat's theorem on sums of two squares, which is one of the most beautiful laws of prime numbers. Let's explore beautiful laws of prime numbers. See you next week.